think it's time that we get started. We're here with Suchi, Saria, and Adarsh Subbaswamy from Johns Hopkins, who are going to talk about subtle biases in data and the reliability of machine learning, focusing very much on how we make machine learning systems more reliable. So with that, I will turn it over to them.
Thank you so much. I am very impressed with folks being here at 5 p.m. in the evening. This is a very hardworking community. I feel like at 5 we should be heading out for drinks and dinner, but it's going to be, hopefully it'll be fun. It'll be worth all the time we spend here. And we've certainly spent over, I would say, nights, many, many days and many, many nights on this tutorial, so I hope you'll appreciate it. So the topic of this tutorial is sort of in part inspired by, over the years as I've worked in machine learning, and I work extensively, both sort of in core ML and in particular, our lab does a lot of work in safety critical domains like healthcare, where essentially it's costly to be wrong. And in that scenario, essentially the question is, how can we take machine learning algorithms that we build and use that to both measure when it's behaving in unanticipated, unreliable ways, and how can we then design objective functions that allow us to be reliable. And sort of we've been doing this over the years in one-off ways and have written some on it. And then parallel, there's a movement happening in the last year and a half, and in particular, nationally, there's been a lot of effort, especially in the last year and a half, through the national academies, in imagining how do we broadly communicate across fields in understanding as AI impacts them and their disciplines, what can AI do, what can AI not do, and how will it get integrated, and what's the impact it'll have. And in these meetings, one of the things that's really concerned me is that there are people who are over-enthusiasts, so they think it's super exciting, and on the other hand, there are people who are pessimists because they're sort of really confused and concerned and unsure because of so it's very important for us as a field, especially as machine learning is moving from practitioners who built the methods themselves to more users. And this meeting, for instance, exemplifies this scenario where as you start interacting with other fields, there are other considerations that drive what should be prioritized within the field. And so this whole talk is my effort at trying to consolidate work within the field and understand and taxonomize where are the gaps in building and understanding reliability. And that's really what most of the talk will do. So I started by saying, this is ML that's making its way across many disciplines, machine learning, healthcare, disciplines that we study here to some extent. And, in these meetings, what I notice is essentially, view from the outside. This is sort of practitioners, users of the field sort of see this and think of ML as right now their view of ML, their view of AI is kind of this magical wand. It's like the bridge to the future. We're going to use this and all our problems will be solved. And it's not really their problem. In part, it's because of all the advertising that sort of pitches it as something that is very robust, reliable, ready for use. But if you've actually built these techniques, I kind of feel like my daily use is more like this, which is, I feel like you have to be really aware of the idiosyncrasies of how something works and where it breaks and why it breaks and when it breaks, and it's, so it's certainly true in most instances when somebody says, can you do this? The answer is typically, yes, we can. But when we're saying, can you do this? They're thinking, amazing. And in our head, we're not anticipating the fact that they're thinking, the bridge is there to be built. It's all good. We know how to build it. We're thinking sort of what is it going to take? And so when we say yes, what we mean is, done. Our field has this culture where essentially you train and test on a fixed data set, and we write a few papers, and we say, we've solved the application, moving on. And, when you look at a production system, sort of model is one module of a larger system, the environment involves, models often misspecified, or even if they weren't in the beginning, they can become over time, depending on how the domain evolves. And overall, sort of this understanding of like, this notion of like you're building a system, but really the components are very accident prone. So there are many forms of error, many types of failures, and our understanding of what these types of failures is extremely limited. And that makes it very scary when you start using it in the real world and other people are reliably like depending on you. And essentially, you need to have an understanding of like how are you going to maintain, manage, and guarantee it. So 2016, this paper was written by like several folks on the West Coast, and this paper sort of characterized what are concrete problems in AI safety. This to date, I would still say, is one of the most thorough and well-written papers on the topic. It's very elaborate, and it really emphasizes and covers sort of core areas, but with a huge focus on reinforcement learning, which is interesting in the sense that, in RL, agents also can have a will because they explore, and so there are multiple ways in which RL agents can behave that you might not have anticipated. But I'm actually going to step back from RL and speak more about outside of RL, like classical majority of the fields that are actually using it in practice are more around classification, regression, kinds of problems we discuss here. And in thinking about this, one thing that sort of completely surprised me is, apart from techniques to solve a concrete problem, we don't really have a framework. We don't even have a framework for thinking about this. And sort of the question is like, what are the design principles? How do we even go about figuring out how to attack this problem of failure? And is it sort of right now the field looks like a compendium of papers. And so basically here we're deriving inspiration from other fields which are safety critical, like aircraft maintenance or building bridges, civil engineering or nuclear engineering, where people have over the years developed an engineering discipline. And this discipline incorporates like a notion of safety reliability. And there's a very clear understanding of like good principles. And these good principles aren't just NeurIP-style papers, right? They're sort of more elaborate than that. So effectively over the last 2.5, 3 years, and so beyond building the methods, in the last 2 years in particular, we also started building real software that now is going with side of hospitals that, physicians are using and practicing with, and it's meant, the urgency, the need to think harder about these issues. And so that's in part like motivating the rest of this talk. So here are three key, pulling ideas from from the field of reliability engineering. Here's sort of one way in which we think about like grouping, approaches to reliability. So first is this idea that you want to prevent or reduce the likelihood of failure. So before you're going to build a system to do something, you're going to sit down, and the first bucket is sort of this notion of like approaches to prevent or reduce the likelihood of failure. And think of that as like overall what we'll call failure prevention. Second is this notion of identify failure and the causes when they occur. So as it's being used in the field, you discover why a failure has happened, do root cause analysis to determine, and like one set of tools is the 5 whys, and then come back to see how that might then change the way you do the third thing, which is you fix the failures when they occur, and then what's the maintenance process? Like how does it get maintained over time? And so these are failure prevention, failure identification on the go, and that reliability monitoring, and then maintenance, okay? And so these are sort of the 3 tenets we need to be thinking about. And as we're thinking about it, let me draw sort of in machine learning, what does it mean, okay? And sort of in particular, when we say machine learning, I don't mean the systems components, because systems people, like the software stack, the networking stack, there are tons of people who are thinking about that in other communities. I mean the data layer, like the part that deals with the models. And so here, effectively, what does failure prevention mean? So can we improve learning methods to be less failure prone or accident prone, right? Can we build methods that are to be less accident prone? So we need to figure out, what do we mean by accidents? What do we mean by accident prone? Second is, can we improve evaluation documentation reporting to prevent misuse? So these are sort of both under prevention, okay? So the next part is reliability monitoring, which is, as it's being used, are there approaches by which we might detect likely mistakes at the time of use? And can we identify when the system is becoming stale and it needs to be retrained? When should that happen? And the maintenance piece is, what should the method for updating the system look like? Okay. And so from from a point of view of sort of how we're going to scope this talk, so much of the talk is around discussing these principles for enhancing. The goal of the talk was to pull structure into the field and discuss principles for enhancing reliability and preventing failure. The talk isn't going to be a deep dive, except for some areas where we will at least give you some technical content. Overall, there are like very deep dives in, say, for instance, reliable decision making, which I've relegated to other talks and can point you to if you're curious. Related ideas here in the community, people have published under robust and trustworthy and accountable and reliable and safe in varied ways, and so we'll sort of we'll pull ideas from there, and the focus is on supervised learning, prediction, classification, regression, less on RL. And then here's one that I think a lot of people miss. So right now, again, the other issue that's happening is, especially, say, in fields like healthcare, where there's a very large, robust discipline of practitioners who already do analysis of data. And now we're moving from doing offline analyses of data, which is, say you were given some data set, you were trying to analyze to see some effect held or not, to a lot of machine learning systems are looking to deploy products within workflow, right? Deploy it for use in real time. And that's actually a pretty big shift in the way people need to think. And so even if you take the same classical methods, there's this huge misconception in the field that if it's a tried and tested method, they think deep learning, in particular, is new, understudied, and therefore susceptible to these kinds of failures. On the other hand, classical tools, as long as you're building systems using classical tools, you're completely fine. Like, you can deploy them, no worries. And effectively, the point I want to drill down, especially even if you're using classical tools, as long as you're building these data products and deploying them, much of the concepts I'll talk about here is relevant. And then in terms of approach, when extensive literature exists, we summarize key approaches, we speculate about open problems when there isn't a whole lot, and then to declutter, fuller set of references will move to a reference doc. We don't try to be exhaustive or even attempt to be comprehensive on the slides. So I'm going to cover each area one by one in detail. All right, so the first one, failure prevention. So what are the key tenets of failure prevention? So ideally, when we're trying to prevent from failure happening, the goal is we want to proactively identify likely sources of error and then develop methods that proactively correct for these, right? So let's identify sources of error and let's correct for these. So first, what are common sources of error? Okay, so we're categorizing them in these four, I would consider, groups that actually describe, I would say, large categories, and then of course we may discover new ones, in which case, to be augmented. So the first I call bad or inadequate data. So let's look at what do we mean by bad or inadequate data. So this example has been talked about a fair amount, and especially in this community, people are probably very familiar with it. This is sort of the bias in face recognition, where a system was used to do face recognition, and various different companies, a study out of MIT Media Lab, and effectively multiple different systems, and the performance was compared, and overall system performance was great. But when you look at specific subpopulations, so for instance, its performance is really good at darker males, and lighter females, but abysmal for darker females. And the issue is this may have downstream ramifications depending on what the system is being used for. And so I would consider this to be sort of an example of inadequate data. So first of all, why are we trying to taxonomize the types of errors? Part of the reason to taxonomize the types of errors is because that then motivates different types of solutions to tackle each type of error, right? So that's one of the reasons to do it. And I would say broadly in the community, there's sort of a little bit of a confusion about when people talk about bad, at least what I'm seeing is when people talk about errors, they're basically right now there's machine learning systems that work and then everything else is just bad and biased. So there's no sort of language that is more refined than this is biased or this is bad. And what we want to do is move away from the idea of using bias and bad very broadly and sort of splitting it into little groups. So in this particular case, this is an example of sort of a type of error that's happening because there's just not enough data. That could be because there's not enough data on which you trained or you need to change your data collection. So for example, in this case, you might say, take your data, you can measure performance in some populations of interest. What you discover, so in this case, instead of measuring overall performance, if there were special subpopulations of interest and you'd measured performance, you'd have discovered that it performs poorly. And then you might say, well, what if I don't know these subpopulations of interest up front? So then what people try to do is they say, okay, let me try to cluster my input space into regions of high density and low density, and then identify in regions of low density if there's correlation with any attributes that are important and sensitive, right? And then the solution might be, and the solution in this scenario is, well, regions of low density, you need better data. You need better, more representative data. One another thing people try to do to fix this is to have a different objective function, where basically the idea is you kind of upweight the data that aren't as present and like you downweight the data that are present like you have too much of, so that the model learning knows to focus on and learn the areas that there hasn't been enough data for, right? So that's an example of inadequate data. What's an example of bad data? This one is a little bit more subtle, actually quite a bit more subtle. So if you've read Freakonomics, you've probably heard this, which is there's sort of this idea that goes around that taller people are much more likely to be CEOs. Or in other words, if you're shorter, your chance of being a CEO is much lower, right? So what does this mean? So let's say you're a biologist, and you might say, hey, you know what? Actually, maybe there's truth to it. Maybe there are genes that are attached to, height, and then there are similar biological material that then informs your skill level in certain areas that are highly, predictive, or predictive is not the right word, that then dictate whether you're likely to be CEO, right? So here's a graph that defines this. So here in this case, I'm just sort of, this is a cartoon figure. Let's assume closed world. I have a collection of genes. Gene influences height. Gene influences IQ. Genes influence EQ. And then your IQ, EQ, but not your height. Let's say the world looked like this. Your IQ, EQ, turns out affects your ability to be CEO. So far, so good? Nods in the head. Yeah. But then your ability to be CEO means if you're likely to be CEO, then means you're is CEO. So there's difference between, there's notion of like your ability to be CEO versus your is CEO is notion of, well, you're capable, but you don't want to be, right? That often happens. Or you're capable, you have family constraints. Any number of reasons, but these are two different variables, right? One is your capacity to be, second, you're choosing to be. Okay, so I take a problem data, I get a data set. In that data set, I have height, and I have who are CEOs and who are not CEOs, right? That's common. I get a long data set Excel spreadsheet like that, and this is my model of the world. Let's say this is the truth. This is the model of the world. Now, I get this data, and this data I want to compute, is height associated with being a CEO, right? And if the world indeed looked like this, and you had sampled from this data, from this graph, you could have actually answered that question. All you need to do is correlate the two, and if so, all that's saying is, yes, there are influence paths, and this is capturing the number of influence paths that suggests that indeed there's a correlation which has to do with your biological material. So the point is, the question can be answered if indeed your data were generated from a world like this. But here's the deal. That's not how your data is generated. Your data is generated from a world where there is an edge like this. And this edge is basically, for a fact people are biased, because people do look at taller people and sort of get, sort of intrigued. And perhaps there's sort of like well-documented notion of people being more likely to, recruit and give a job of a CEO to somebody who's taller. Which means if your graph is indeed this, and your data generating process, all of the data that you have is coming from this graph, your chance of being able to answer this question using this data is not possible. You can't get it done. And the reason you can't get it done is you're trying to answer whether there is a backdoor path that there's a correlation between this through the biology, but your actual data has this, and there's no way to disambiguate the two. And the only way to disambiguate the two would be if every one of these variables that could possibly link them were also observed. Okay? So far, so good. So reason this is important is a lot of times when we have data problems or when people are trying to answer questions, in many cases it's sort of an issue of not just bad data, it's that the question can't be answered at all under the scenario in which the data were generated. Okay? And it's important to distinguish between when the answer cannot be answered at all versus it can be. And in this case, if you somehow, this was the truth, and you could measure both IQ and EQ, so it can be answered in this scenario, but if you could measure IQ and EQ, you could indeed answer these questions. Okay, so let me summarize for those of you who are not as familiar with graphical language literature. So if EQ is not observed, IQ is observed, and in the real world, the data was collected in a scenario where CEO is, tends to be recruited if they're taller, you just can't answer the question. But if, for instance, all of the backdoor paths were closed, blocked, then you could maybe answer the question. Okay? So far, so good. So the notion of what can be answered itself is subtle. And here's a terrible example that got a lot of press, which was all around somebody taking an image and basically doing face recognition and based upon that guessing what your profession's going to look like. Amazing. And that was basically an example of this, which is that's exactly this corollary, except instead of height, you're looking at facial features instead, right? And that question in today's world just can't be answered. So you shouldn't attempt it. So that's an example of bad or inadequate data, right? So you could go, in some cases, in bad data, you can go collect more data. Inadequate data, you can collect more data. Bad data, you can't change your question, go do something else. Okay, so what are the other types of errors? So second type of error is differences or shifts in environment. This is one that is catching more interest, but it actually is surprisingly prevalent, and it is a type of error that is quite harmful in many, many scenarios. But here's the cool part. We can actually account for these. So these are scenarios where you can often do something to fix it. So I'll actually do kind of a deep dive into this section because this one I feel like there's an enormous opportunity to bring these techniques to bear in a much larger set of problem domains. So let me start with another example. This was a recent example that was published where the goal was you have X-ray images and your goal is to diagnose pneumonia, okay? And they used X-ray images from multiple hospitals. They developed a model using a large data set, and it was across multiple departments, multiple hospitals. And what they found was when the model was evaluated beyond that data set, so let's say they took 2 or 3 hospitals, several departments, but when they evaluated in a new hospital, a new set of departments, these were all New York hospitals, the performance degraded, okay? So you might say, why is that happening? Okay, so this is like, it's biased. Okay, let's try to figure out what's going on. So, turns out, X-ray has style features. So in this case, on the right, on top, you basically have 2 things going on. One is like, because they have to notate the orientation, whether it's the child from the front or the back, or right or left, they basically have an imprint here that tells you the orientation. Okay? But simultaneously, the way that imprint is done varies across hospitals or varies across departments. And so essentially, this question of, so what was happening was that basically you were given a data set, and in that data set, the model learns an association between pneumonia and these style features, even though the style features shouldn't at all be informative. It's really only the fact that the orientation and what's actually in the image. So then, one point to that would be, okay, well, can we just ignore the style features? Can we take it out of the, can we take that part of the image and can we black it out? And the point is we can't just do that because we do need the orientation information. So this is an example of the fact that across hospitals, different doctors are using the product. Each doctor has its own style. And because of the fact that there's a different mixture of styles across these different hospitals, there's this subtle association being learned that we would have liked not to learn, but that association doesn't transport or doesn't go over from one to the other. Does it make sense? And that's an example of a shift. And a shift that's, and shift causes a point of failure, which is you expect the system to work and it doesn't work. right? Let's do another one. This is an example that the community is probably quite familiar with, which is predictive policing. So predict when, where crime will occur. Then you deploy a system and you send police to that same area. The more you send people there, the more you detect. The more you detect, the more you train your predictive system to keep discovering that same area as the place where all the crimes are, and this thing has a major feedback loop, right? So that's a major problem. But turns out, actually, predictive policing is an example of something that's also called a shift, and we'll talk about what kind of shifts. So these are examples of different forms of shifts. These shifts are very prevalent in a variety of different scenarios. And the questions we're going to ask now are, can we learn models that are stable to shifts? Stable means invariant to shifts, okay? And there's large literature tackling shifts. We're going to think about the notion of shifts in the context of failure prevention, okay? So a lot of literature in the ML community that has dealt with shifts tends to be, quote, reactive. What we mean by reactive is you use unlabeled samples from your target distribution to optimize your model, right? So you have domain one, you have data from here, and then you say, okay, shift means I have a new data set, like from a new hospital, and what I'm going to do is I need to somehow adjust to this new hospital, so what I'm going to do is do some kind of reweighting technique. And then there's a variety of techniques people have come up with, but each one of them is doing this version of, I have my source data, and I'm going to take my target data, and somehow I need to do transfer and adapt to these new distributions. The problem is, obviously, if you are building failure-proof systems, imagine deploying a system, you don't know what all the, it's hard to anticipate what are all the test environment data, right? It's hard, the environment evolves, being able to have access to all of the different kinds of test environment data that you need to be failure-proof to, that's actually quite hard. And you want your predictive model to not have catastrophic failures and to be able to generalize in new and unseen environments. So with that, so instead, I want to sort of think of this sort of contrasting paradigm of what I call proactive shifts. So proactive means here you learn the model to protect from likely problematic shifts. So can you anticipate what are likely things that can happen? And then if so, can you build methods that protect from it? Make sense? So, all right, so the question is, well, what does that mean? What do we mean by proactive? How do we recognize whether something can be done? How do we build methods that do that? Okay, so I'm going to do a little bit of a deep dive here because I think this is really cool and, like I said, very broadly applicable. So first thing we're going to do is to represent shifts using, so first we need a language to talk about shifts, because right now it's just things change, but things change are not amenable to analysis and not amenable to any computational models. So first thing we're going to do is come up with a way to represent shifts. As soon as we have that, we're going to try to come up with specs. You want to come up for any given problem domain. You want to identify which shifts are you trying to protect from. That involves kind of understanding the domain and anticipating sources of failure. Okay? Now that you know what you're trying to protect from, what the failure sources might be, and we'll talk about how do you spec that, we're going to basically implement proactive learning methods where the idea is it takes the graph, comes up with the specs, and outputs what parts of the data distribution to ignore and what not to ignore. In other words, it's a learning protocol that guarantees that the resulting models are actually safe, failure-proof, to the kinds of shifts you discussed. And now we fit these, and then finally we'll discuss the optimality, soundness, completeness guarantees. Okay? So let's do one at a time. What do we mean by shifts, and how do we represent them using graphs? So here's a simple example. You're looking at smoking habits now, and your goal is to predict how does smoking habits influence your probability of seeing what's the probability of cancer in the population 2 years from now, okay? And so this is obviously forward in time. Smoking, we know, is causal for cancer, causes cancer. And so this is a well-founded question, smoking habits now, and this is sort of a relationship that you can learn. And now let's imagine there was a smoking ban, okay? So President Trump got hold of this idea, and they thought it was very important to go fix this, and say they actually stopped Juul use. And now Juul use was stopped, and the question is, now you're trying to figure out 2 years from now, so you're trying to apply it to a new regime where people use Juul a lot, and now they don't use Juul a lot. So how do we represent this shift? So basically, X is your inputs, which is smoking habits now. That's what you've captured using X. Those are your inputs. And T, your target, is basically frequency of cancer. So you're trying to predict what is the probability of cancer given your inputs. So far, so good. And here, this relationship of T given X is what I call stable. Stable means it doesn't change over time. what effect Joule has on cancer doesn't change. On the other hand, the prevalence of people smoking Joule changes. So that's a version of like this particular edge is unstable, but this is stable. And so taking it one step further, this is what's called a selection diagram. And in a selection diagram, you have input and output, and this is a classic graph you've seen before. And then whatever is likely to change, we put what's called a selection variable on top to indicate that. Okay, so let's do an exercise and a few more. So another common one people talk about is label shift, where you have a notion where your T, this should have been, by the way, pointing this way. I hid a few Easter bunnies in there so you discover when I'm not making sense. So this particular thing should have been pointing this way, but basically the idea is this thing is an example of a place where T is changing, X is stable, this relationship is stable, and that would be a notion of a target shift. Okay, so let's go back to the pneumonia example. So in the pneumonia example, you basically have pneumonia. So which department you're in or which doctor you are, that's D. And then T is whether or not you have pneumonia. F is whether or not there are basic specific style features. And X is the lung X-ray. So let's talk about how we got these edges. So which department you're in and sort of has an effect on like basically whether or not you, like what fraction of pneumonia cases are being seen. Okay, so that's this. And then this edge is basically, given the department you're in, they may have a certain style by which they use to imprint that orientation. So that's right here. So that's basically this edge. And then what this edge is saying is given the style and given the patient has pneumonia or not, that's what the X-ray finding is going to look like, right? So the type of pneumonia they have influences what the X-ray looks like and the style feature itself. So far, so good? If you're confused, raise your hand. I will do something non-traditional and take a question in the middle of a tutorial. Okay. So, so basically, we have this graph, and then we can apply the same ideas. Basically, here in this case, we were saying this particular thing is unstable, or it varies. You know, the way people imprint varies by department, depending on the types of docs that are in there. On the other hand, how pneumonia affects X-ray has nothing to do, you know, that's a stable relationship, right? It doesn't change. That's independent of department, et cetera. And then similarly, you know, prevalence by department, these are all New York hospitals. There's no reason, there's no explicit upfront reason for one to prefer one hospital over the other in terms of, you know, why pneumonia patients should go more to one hospital. There's no reason to believe that, so this is also stable, okay? So you have a graph, you've quantified stable relationships, and now to use a selection diagram, I'm just going to basically put an edge there pointing into F. So far, so good. So essentially, all I'm doing is a little exercise in showing how I can take hard graphs and turn them, write it down using a selection diagram, and figure out what parts of the graph are changing. And you might say, well, these are really simple examples. Does this really work in complicated examples? So like I said, my lab works a lot in real domains in healthcare. This is an example of like basically how INR, which is a lab measure of, you know, the amount of clotting in your blood, and all of the things that influence it. And here in this case, we sort of maintain both the things that influence and then what are the selection variables we are worried about. And we want to, like, what are the kinds of changes we are worried about? Shifts that can happen as you deploy a system from one hospital to another or one department to another. And we want to make sure we don't want our system to break if these shifts happen, okay? And so this is one graph, but you're thinking, oh, that still doesn't look complicated enough. Well, turns out this is actually part of a much bigger graph where I just showed you INR, but in reality, we have over 30 variables, and this is like a continually evolving graph where as we learn more, we sort of do this, and this is kind of like our way of failure analysis. So essentially, this is something that scales. And in fact, even the predictive policing example that I spoke about is an example of same shifts. So right models, so here the idea is, turns out you can think of that as a form of shift called policy shift. I won't go into details here, but what have you learned so far? So all I said is, I want you to be motivated to understand shifts, okay? And second, if you are now motivated enough to understand shifts, which you won't just get through the literature of this tutorial if this is the first time you're hearing it, but if you watch it for the third time, it'll hopefully make sense and read some of the pointers. But the point being, these shifts are everywhere. Shifts very much make your models prone to failure. You want to represent these shifts using graphs, which is a language for writing down these shifts. As soon as you write down these shifts, now we're going to try to figure out do we leverage these graphs in order to learn models that are failure-proof, okay? So second step is you have these graphs now, and you've figured out what you want to be invariant to. So in this particular case, I want to be invariant to the style feature. We already did this for pneumonia. And so now that we know what we want to be invariant to, and you can do that same thing in sepsis, right? You can choose what you want to be invariant to. Now, here's the cool, magical part. You put this graph, which has both the variables and that you're going to, the input graph, as well as the things you want to be invariant to. And what this algorithm does is essentially takes this as input and outputs two parts. One, what are parts of the graph you want to learn, and what are parts of the graph you want to ignore? Okay, so it takes this complicated domain. You can do this for any domain. Once you have a domain, you write down your variables, your inputs. What it's saying is what part of the variables or dependencies do I want to learn and what I don't want to learn, okay? And so these are components to learn, and then whatever it has sort of chosen not to include, like influence paths not to include, those shouldn't be learned because they capture unstable relationships. And what this tells you is both what parts of the graph to learn and how do I combine them in order to get my final output T. So in this case, my goal was to output T. These were my input variables. It tells you if certain variables are bad, it'll tell you to ignore them. It'll pull out which variables to consider. So now that I have these, amazing. It's basically a pre-processing step. You can take your classic favorite deep learning algorithm or whatever, depending on the type of data. So for instance, if it has sequential data, you may want to train a sequence model, or you may want to use, models for sections of the data, images. You may want to use models that are suitable for images. But essentially, you can now choose each of the portions of the data that you're trying to fit. You have the flexibility to fit it as you'd like. So this is using a classical learning techniques, you can fit them. And if you do this, essentially what comes out of it is your final model. And what that does is now the resulting model has some really nice properties. So the first thing is that it's distributionally robust. I'll explain what that means. That means in failure, when we're trying to do failure prevention, what we want to do is to be failure-proof to arbitrary shifts, right? To any shifts that can happen in the environment. And what this is giving you is a model that is basically the best performing model under arbitrary shifts. Okay, so there's essentially the best performing model under arbitrary shifts. So there's, so essentially you can sort of do this and be happy that there wasn't juice that needed to be squeezed out that you couldn't, okay? And furthermore, so that's sort of the first part, which is the optimality piece, which is this gives you a high quality model given the set of invariances you need to protect from. The second aspect of this is that the algorithm itself is sound and complete. So what do we mean by that? That means in a case where it returns this distribution, these are the things to fit, and here's a way to combine them, it is correct. It will give you, it essentially gives you guarantee that you're essentially not going to, you are actually going to be invariant to the things you specified you wanted to be invariant to, which is really nice. And the flip is also true, which is if the algorithm comes back saying nothing can be done, that literally means nothing can be done. In other words, there does not exist another way by which you can figure out, like there's no shortcut here. There isn't a version where you can say, well, can I do something else? And can that then help me, can that then help me determine sort of an alternate model that would be stable, okay? So if you want stability, it's saying it's an if and only if, which is really nice. And it has corresponding optimality guarantees. Now, you'd say, well, this is kind of silly. Is it really the end of the world? Can I still not do anything? Turns out there are two things you can do if you're willing to be creative and industrious, which is if you can go collect your own data, then it can guide your data collection. So for instance, when you look at the graph, if there are certain variables that are basically hidden, it often prevents, there are hidden variables or variables that induce confounding, you can essentially go measure those variables. And if you can measure those variables, suddenly you may be able to become invariant. Okay, so that's in that example that I gave you of the height, CEO height example, like going and measuring EQ and IQ would have been that version of that answer. okay? The other thing you can do is maybe what you realize is in general, if I want invariance to these assumptions, I won't succeed, but maybe you can make some additional assumptions. So for instance, I don't want worst case performance against any perturbation. Maybe I know something about my domain, so I want to assume some kind of perturbations for some of the shifts that I'm talking about, right? So in which case you can do better. Okay, so to summarize, essentially, there are all sorts of shifts in your environment. You can now start thinking about how do I document and represent these shifts? Can I now think about whether my algorithm, regardless of how you fit the model, you can basically use this approach to test whether your model is sensitive to these shifts, and you can measure it. And you can also use this this surgery estimator for figuring out alternatively what's a different training procedure, which is a pre-processing step that tells you how to fit it instead so that you get these kinds of invariance guarantees. Okay, and collect data if it turns out that your question can't be answered given the current data. So, okay, so sometimes the question I get asked when I present this, this is very recent work, so in recent time when I was presenting this, a question someone asked me was, well, what happens if I have a complicated domain like mine? And the issue is, I don't actually know what the graph is. I don't know what the right graph is. And so I wrote down a graph, but I don't know for a fact it's the right graph. Well, it's okay. What you're going to do is to write down all possible graphs that you think is reasonable. In other words, you can write down a graph and then you say, I don't know if this edge exists or doesn't exist, you can remove it, okay? So you can write down multiple graphs, and for each one of these graphs, you can check sensitivity and it'll sort of spit out for you what the parts of the graph you should care about. So that's one. Second, if that's the case, then you can see, okay, I can do some risk assessment analysis, which is what's the likelihood that this graph is the more correct graph or that graph is the more likely graph. And based upon that, you can choose the extent to which you want to care about, like basically hedge your risks, right? Which is something that in any real domain, we have to think about, well, how likely is something, and then figure out what you want to protect against. So this is sort of, I think, a brand new path for starting to think about how do you take hard data sets and move beyond the conversation beyond it's bad data, it's just bias, to what are places where we can actually fix things and do things versus what are places where we can't. And just there's nothing to be done. Go either collect better data or go measure new variables or change your problem specification because it's not possible to answer them at all. Okay, so Adarsh is going to talk about some of the other methods.
So just remember that what we're trying to do here is build reliable systems by preventing failure. And so the way we were doing that was we were saying, what are common sources of failure? And so we've just talked about two instances where the types of failures are sort of inherent aspects of the data. Obviously in the bad or inadequate data case, but then also when you go from a training environment to a deployment environment, which has data that's generated by some shifted environment or process. So now we're going to look at model-associated error. So how the very act of choosing a model and then also how we choose to fit the model can result in failure. So we're going to cover two main types. One particular example is faulty implicit model assumptions. So when you choose a model, it actually comes baked in with certain assumptions that it's making. And it's really easy. It's an innocent mistake to just, oh, this is my favorite method, or I have this suite of methods that I use, and not to consider the particular assumptions that are being made and how relevant or applicable they are to your problem. And so one way this can occur is if you're in a complex domain. Let's say we're modeling a biomarker like blood pressure, and we're interested in predicting the effect of some treatment. So we're doing treatment effect estimation. And there's all sorts of factors that are affecting blood pressure, and there's interactions. And so we're in clearly a very highly nonlinear scenario. If I just go and I fit my linear model, one thing I have to watch out for is by default, my linear model is assuming that there's no interactions. And so it's sort of this simplified version. And what that means is that my results that I get might not be reliable. So if I try to make decisions based off the effects that I'm estimating, I have to be careful and make sure that sort of the model is well specified for the task. Another common thing is we like to assume that our data is IID. And so there's independent errors, and there's certain domains where this just isn't true. So in social network data or in housing data, often what's happening is people in the same communities or neighborhoods actually have associated outcomes. And so doing one thing to one person actually has effects that spill over to other people. And so most of the time when you're fitting models, you're assuming independence. And so the resulting conclusions and decisions you make will be wrong. And so the point here is that we want to be explicit about any assumptions that are made, because again, these are implicit assumptions that are associated with model choices. If we're explicit about them, then we have an opportunity to consider the fit between the assumptions and then the actual domains that we're applying these to. And so we'll actually address this more in another section. The other case that sort of we wanted to highlight and pull out is this notion of model fragility. So you might imagine that I've trained an image recognition system and I'm really happy with it. It does well, and so I give it a picture of a panda, it tells me it's a panda, I'm happy. But then someone comes along and just slightly perturbs this image of the panda, where to me it's still a panda and I can't tell the difference. But now when I feed it into my model, it's the same model, slightly different image. Now it's telling me that it's a monkey. And what's even worse about this is, so first of all, now I'm wrong. And so this is bad. But what's even worse is, in this case, we're very confident in this prediction that it's a monkey. So we're confidently wrong. So now there was a failure, and if we think about sort of the goals, we're confidently wrong. It's going to be hard to even detect that there was this failure. So that's why we want to think about, okay, how can we even prevent this from happening? Because these sorts of errors are going to be hard to detect. One thing to note is, like, we're talking about perturbations of inputs, and this sounds like shifts, and we just heard about them. But this is actually a complementary idea. When we were hearing about dataset shift previously, it was this, those are correcting sort of issues with the data. This is a property of fitting a model, actually. And so there's been a lot of work in studying adversarial examples like this because of the popularity of neural networks and the fact that when we're dealing with high-dimensional inputs, there's lots of opportunities for these sorts of sensitivities to shifts. And the fundamental property is if there are small perturbations in my inputs, it doesn't make sense that there should be really drastic changes in the outputs. And so we don't want models that are super sensitive to this. Like, the engineering analog is to think about the structural integrity of a building or a bridge. I want it to stand up to the wind, let alone a breeze. But if we're so fragile that a breeze is going to knock everything over, then we need to be careful. And so thinking about how can we make sure that a model we deploy is going to be strong. So this motivates procedures for training models that are robust. And so we want to make sure that through the training procedure we've protected against the kinds of perturbations that these slight shifts. Additionally, it would be nice if we could get performance guarantees, not just sort of training, but then can we actually certify that what we're doing is correct? And so in adversarial training, what we do right is we pick the right objective. So now we know that I'm not just interested in performing well, but I know that if perturbations come my way, I want to still perform accurately. And so I want to make sure that I account for this in my objective when I'm training so that I'm minimizing the possible bad impacts for the perturbations if they do occur. And so it's the similar idea of worst case analysis. I want to make sure that I'm mitigating the bad impacts that would occur from changing the outputs. But the point is just training with the right objective isn't enough, because we know from fitting our models that our training error is always less than our population error, which is the thing that we were interested in. So there's no guarantees that this model is robust, even if I'm training with the right objective. So that gets us to now talking about training with guarantees. And so people have done work on trying to train where at the end of training you have a model which can actually give you what is called a certificate of robustness. And so this is nice because this is a value dependent on data that tells you sort of how bad the worst your error could be for the types of perturbations that you were trying to protect against. And so it's a training procedure that now gives you model guarantees. against these sorts of adversarial examples. A related idea, now instead of training, we can also think about testing correctness of models. So here, this is talking about verification of neural networks, where what we want to know is, will my model act correctly on these inputs? So I have an input-output pair, and I'm saying if inputs of this sort are shifted in these particular ways, will the outputs change? And so this is a yes or no question. Right now I'm not talking about performance, I'm talking fundamentally about the behavior. Will things change? And so getting exact answers to this is it's a really strong statement, and you can be very confident that, oh wow, this model is robust to these sorts of failures. And there's lots of interesting work in this that's but the issues are sort of taking techniques from software engineering, where it's been common to do formal verification of systems, and translating them to neural networks and large data sets and all these sorts of problems. Exact computation is slow, and we have scalability issues. And so there's recent work in trying to do this. But what I want to emphasize about verification is the fact that this is a testing procedure. So you have a model, and now you want to test and say, does it perform the way I expect on this set of inputs? And so testability is another good property we want. In addition to, say, performance guarantees, we also want to know, can I test my model before I deploy it to make sure that it behaves as I expect? So beyond data, beyond modeling choices, fundamentally, there's issues associated with the fact that we're building machine learning systems that interact in a broader context. And so it's a model is one piece of a system that's, say, in a decision-making process where there's users who are humans. And so there's issues associated with poor reporting, and more generally this concept of communicating well, communicating in order to prevent failures due to misuse. So a common thing is machine learning models are actually pretty narrow. If I train an image recognition system, but I trained it on cats and dogs, then I have a model that distinguishes between cats and dogs. And at that, maybe it distinguishes between cats and dogs. But it's very dependent on sort of like the data I fed into it and sort of what I actually trained it to do. So there can be a mismatch between the actual task or the intent for a model and then how people use it, because perhaps they don't know and it wasn't communicated well. And so that's what we're talking about in terms of poor reporting causing failures, where you're using things in ways they weren't intended to be used. And that's just a great way to go and cause failures. So the works in this section were motivated by the fact that in other high-impact domains, like clinical trials and transportation, there are standards, regulations, and protocols for documenting things to make sure that sort of we don't have these kinds of mismatches. And so one idea is to sort of think about data is a fundamental unit for training a model, right? Without data, I don't have a model. And there's relevant aspects about the data set that inform like whether or not this is the right data set for me to use. Is this something that makes sense? So like, what is the data set's purpose? Why was it collected, and did they have an idea of what they wanted to have done with it? Similarly, we want to know things about how the data was collected and processed, because if there's bias in how the data was collected, selection bias, reporting bias, I want to be cognizant of that when I'm training my model, because my model will inherit those same biases. Was there measurement error? Maybe this data set just isn't reliable enough for me to use. And so it's about, again, explicitly listing and communicating pieces of information that you need in order to make decisions, in order to make good decisions about your models to avoid failures. And so these are taken from this paper, Data Sheets for Data Sets, which sort of lays out a framework for what might this sort of documentation look like. And so here we've taken some segments from an example data sheet where we say what was the motivation for the data set, and sort of there's all sorts of possible considerations that you might have. And one that I didn't touch on but I wanted to show here was like legal and ethical considerations. There's all sorts of considerations you have to do, and currently there's no sort of standard for even doing these. So there's been similar ideas, data statements for NLP, so talking about sort of text-specific issues that you want to talk about in when documenting the data. And then another idea is a dataset nutrition label, so kind of the thing you see on the side of a box of pasta or whatever, with the idea being that building an interactive and modular framework for sort of what are the pieces that I need for documenting and putting them together. So this is one example piece, and there's other things that you can put. For the nutrition label in particular, they actually have a nice demo online where they view this as an interactive system where some of the sections might have graphics or visualizations of the data that you can actually play with in order to get a sense for, like, quickly, is this data right for me? And so, we can talk about other components of successful machine learning systems. So clearly we have the model, and so there's data sheets for data sets. Now we have model cards for model reporting. And again, it's about intended use. Now with models, it's a trained model, so there's questions about performance metrics, and sort of people are coming to an agreement about the sorts of things that should go in this kind of document. But the question is sort of, how do we determine for a particular task, problem, domain, what are the standards, and who should decide them? How do we decide them, and how do we start enforcing that we actually need these sorts of documentation? And so, as an example of the kinds of things that we might want to add, we've been talking about reliability today and reliability criteria. And so, if there's any guarantees or if there's any tests like verification that's been done, we want to document these because now we have a start for actually sort of putting a small contract, like these are the promises I'm making you about this model. And so now we can formalize a conversation about accountability. I promise these things, sort of what should happen if I don't live up to those promises. And so as a slightly different example of reporting, sort of reporting was broadly about communication. And in many applications, the system is a machine learning system is being used by humans, and they're actually interacting together. And so we have to think about how do we communicate the outputs of the model to the person who's using it. A great example of where this is safety critical is autonomous driving, where you have a human who's a human driver who's going to be in an autonomous vehicle. And what's going to happen is if an obstacle occurs or something bad happens, then control is going to be shifted from the vehicle to the human. And so you want this transition to be smooth because if it's unexpected, the user wasn't ready, then you're going to crash into the obstacle anyway. What was the point of doing the transfer? And so clearly these are high impact failures that are entirely sort of, it all depends on the design of the user interface. And designing a user interface it can be sort of unintuitive. There's some studies, particularly for autonomous vehicles, which say, should you report the internal confidence, how confident the car is in its ability to drive itself at any moment in time? How does that help the user? And in fact, that actually can hurt because you might feel unsafe in the vehicle as a result when you realize that it's driving and it's not feeling so sure about itself. And so then when it shifts control to you, you're like, wow, like what's going on? So it's these are the kinds of issues that sort of you won't get without doing a user study. Another example is like what information should even go in this interface? Like how do you communicate? Prior to doing the study, they did a survey and people thought that visual cues would be the most important thing for alerting in an autonomous vehicle. But and audio cues wouldn't really matter. But after testing with the prototype and then doing a follow-up survey, it turned out that the audio cues were by far the most important and effective thing for them. And so again, these are things that you can't do without planning properly beforehand and making sure that you're designing, and in the design stage, that you're going to communicate effectively to avoid these kinds of failures.
So that sort of wraps up our first section. Second and third are shorter. But that wraps up our first section, which is, what are the common sorts of errors? So first step was failure prevention. We want to start anticipating what the types of failures might be and build methods that are robust. And for that, we spoke about different types of errors. And then for each one, we spoke about what are ways in which we might think to prevent it, right? And I want to sort of take this little ambitious attempt to put it all together. Let's say you're a practitioner, you're trying to build a system, you want it to be failure proof, and the question is, how do these fit together? And so here, basically, one way to think about this is, here on top is, first thing you do is, before when you're even trying to do something, the first thing you're going to do is, can this question even be answered using this data, right? So you're going to write out your graph. You're going to say, is this even possible to answer? And what am I worried about? What are the types of data failure sources of the 4 that we spoke about am I worried about? And like define the kinds of invariances you need, or kinds of guarantees you need, or kinds of safety checks you definitely need in your domain, okay? So that's step 0. And then once you've done that, the next thing you do, now that you've determined this, you basically are going to run this procedure in order to be able to come up with sort of which parts of the distribution to ignore and which to keep, right? So that's like sort of check for reliability with respect to shifts, and for, sort of figuring out which parts of the distribution to fit in order to figure out how to be failure proof to those shifts, okay? So once you've done that, essentially you now have these components you were going to fit, and you can fit these. And as you're fitting these, you go into the third type of thing I spoke about, which were those, which others spoke about, which was those adversarial examples, right? So here in this case, any individual conditional you're fitting some rich model. There you might do some regularization function that allows you to tackle perturbations, things like adversarial attacks. And so first you're trying to figure out a question can be answered. Second, you know now what the graph is. You tackle shifts by figuring out what parts of the distribution to fit. Now as you start fitting them, you use the right kinds of regularizers. And again, the field is open-ended. All of these, we're discovering these errors, and we're continually coming up with new methods. And so the best state-of-the-art methods to get around these sort of, to get your fits to be robust, right? And now that you have your fits to be robust, at the time you're doing your fits, you also want to think about model misspecification. In other words, are you susceptible to that? If you've done all of this, then basically your learning framework is far more. You've anticipated far more sources of failure and done something to fix it or address it proactively. Final thing is, essentially, as you move from learning to like now, say you are posting it for somebody else to use, or if you're part of a big system and you're communicating this use to somebody else, then it's responsible reporting. The way, and all of these are sort of rich areas that are continuing to expand. So now we have a handle on what can we do in a preventative fashion. But the question is, can this take care of everything? Is this enough? And so this sort of goes to the second area, which is test time monitoring, which is what do you do? You've done everything you could, you've deployed the system, and the question is now, do you sort of fold your hands and you're ready to go, or is there sort of more to do? Okay, so no matter what you do, there's always new things that can happen that you just hadn't anticipated. And so in this area, what we're trying to do is think about, can we ensure reliability by test time monitoring, okay? And there are 2 classes of approaches, roughly, algorithmic and human-driven. And I'll sort of give you an overview of each. So algorithmic, when essentially algorithmic approaches are sort of, can we use an algorithm to detect at test time a new example is coming in, and when that example is coming in, at test time I want to be able to say my model is used on that input, I give an output, and now at test time I want to detect, was this output reliable or not? It's that version of the panda that we confidently call monkey. I would have at that point liked my test time reliability system to be like, you know what, I think this has been messed with. This is a perturbed example. It was an adversarial attack. I would like to not call this a monkey and sort of abstain, right? So that's basically the idea. So can we do it point-wise? Essentially, each at test time, instead of having a global objective, you're kind of trying to analyze point at a time and assess reliability of the model output at that point. Okay, and so roughly it falls in sort of these high level, and again, many different ways people have thought about it. And so this idea of what's called anomaly detection. So broadly, you can think of it in a statistical sense as out of distribution. So the data was generated in your training data by one process, and now in test time is generated by a slightly different process, okay? And so at test time, when your model is very good at understanding one process, and at test time, now that it's coming from a different process, you struggle with it, okay? So you want to detect that. And so people have tackled that using anomaly detection, which is, something is an anomaly if you will, and there's a broad literature on that. And another name people have used for it is open category detection. So let's say you have, you know how to do cats and dogs really well, and somebody gave you a monkey, and you can recognize that, oh, this is something new. It's a new concept. I know cats and I know dogs, but I think this looks different enough that it could be a new thing. So this is like new concept detection. Okay, intuitively, all of these are examples of like points far away from some known distribution, okay? And then adversaries, like the way Adarsh described, were effectively samples where a model misclassifies that are only slightly different. So adversaries are very interesting. The reason adversaries are interesting is, monkeys look very different from dogs and cats, at least to us. And so adversaries are interesting because, we think it's in a scenario where it actually does a pretty good job at nearby examples, but then it does a poor job here. And so this is kind of, it's not really an out of distribution issue. It's not like it's coming from a totally different part of the space. It's in the same space, but it's something that at that point you're doing a poor job, right? So it's commonly an issue for high-dimensional data, like others spoke about. And then to like kind of sort of overview it all, essentially this idea that new test time, new data is coming, and so we want to think about, at test point, how do we detect when there's something is out of distribution, okay? And I'm going to intuitively talk about fundamentally what are these methods doing, and fundamentally, very generally, sort of. So this is sort of a recent paper that came out in NeurIPS this year, and sort of here's what it does. Basically, on the surface, what I've laid out is data of various kinds. Blue and orange are the two classes. And what it tries to do is develop sort of a notion of exploit what's called the density principle. So the density principle, it's not new. People have written papers using the density principle to try to understand reliability starting in 1992. And the point is, if a point doesn't have too many points around it in the training set, that's effectively the density principle. I'm going to reject it. It means I don't trust it. Okay? So this paper that came out in NeurIPS this year is this idea of, quote, a trust score. And what this trust score does visually is as follows. Let's say there were two classes. There was a blue class and an orange class. For a new point at test time, what it's going to do is compute distance to each of the examples in your training data from each of the classes, okay? So you take the test point, you have a predicted label, and let's say your predicted label was blue. If your predicted label was blue, you're basically going to compute the trust score to the class that is not blue, in this case orange. If it was multi-class, you would pick the one that is next closest, and then compute that distance. And then you compute the ratio, D2 over D1. And based upon this ratio, if this ratio is basically high, you can decide that the trust score is high, so you're going to accept it. Versus if the ratio is low, then you say trust score is bad, I'm not going to accept it, okay? And so essentially, it's a way to, at test time, reject. And what they show is basically by taking advantage of the topology, right, how the points are laid out in your training data set, you can effectively leverage that topology to figure out at test time how to reject a sample, and that indeed improves both on empirical data. They show basically it both allows you to more confidently pick when you think your trust scores are high, indeed you're able to pick real trust points, and then also when your trust score is low, that means you detect suspicious points more effectively than if you weren't to do this kind of approach and naively trust every prediction. Okay? So that's sort of one takeaway. So I'm just going to build on this a little bit more, which is effectively now you can do more than that. So we assumed that, if you do nearby distance, here in this case we just assumed Euclidean distance. If you go in high dimensional spaces, you can have structure. So for instance, you can have very complicated structures, and you actually want to take advantage of both the structure but also how the model, the specific choice of model you have, happen to fit the data. Because some models, like others spoke about, basically if you have model specification or a certain choice of model you've made, that itself is going to perform differently. Its behavior is going to vary depending on the region of the space and how it can fit the data. And so all this is really doing is basically, in addition to the density principle, this is just to give you a flavor of the kinds of test time reliability ideas people are. So this is sort of work we've done where instead of looking at just sort of the distance in Euclidean space, we do two things here. So we're going to take advantage of both the density and the local fit. So one is the test case close to training examples, but also how did the model how did the model do? Like, did the model correctly fit nearby samples using the training data? Okay, so in this case, let's say here's the data, and the data sat on a manifold. This is saying, depending on where you are, you fit a model, and you're essentially trying to see not just, do I have nearby points? You're asking, do I have nearby points by looking at this warp topology, but also, how is my model doing at that nearby point in my training data set? And then by aggregating the two, you can sort of revise the score, and and then this sort of allows you to become even better at doing. This allows you to sort of do a great job of sort of detecting, point-wise reliability. But this is just to give you a flavor, right? Like, these are just starting points of ideas. We could have other ways of now thinking about point-wise reliability. And I think this is sort of a rich area where, like, there are people working on just trying to detect perturbations. And then there are people, and adversarial attacks in particular. But here in this case, sort of more generally, when you're sort of moving away from the distribution, that can be relevant. Let me do one last final example of test time reliability. So here's an example, and this is an example in healthcare, my favorite domain. So here in this case, actually, we can take advantage of this idea in a really interesting way. So in medicine, false alerts is a huge public hazard. Like, there are, it's considered one of the leading, actually, indicator sources of human error and death, because alerts will go off in the, if you go into a hospital, it's sort of the monitors are beeping all the time. And even if a monitor catches that the patient's deteriorating, the alert will just, the beep mostly goes ignored because there are so many false alerts that nobody actually cares. And so the question is, can you actually improve this? And so here in this case, using this idea of test time reliability, point-wise reliability in testing where you have temporal data, at each time t, you have a prediction. But now you do point-wise reliability to decide, do I want to guess, in other words, alert, or do I want to wait and watch and collect some more data, right? So do I alert, or do I hold and just continue? And so this idea, like, you can basically optimize a policy. And so we did this on, large-scale data and show very, very dramatic improvements in reductions in false alerts by doing something like that at test time. So, and so this is cool because, and there are probably numerous domains like this that are sort of sitting around low-hanging fruit opportunity to improve ideas. Finally, for people in the room who are Bayesians, because being Bayesian has become very unfashionable these days, especially, and so I just sort of wanted to make a plug here for people who are Bayesians. Like, I really think the idea of, like, Bayesian non-parametric, this notion of, like, you have a big, large open, the notion of, like, keeping, keeping some probability around for the fact that, like, there are parts of the world you've seen, but there are lots of things you haven't seen. And as new things are coming, you want to be able to put some non-zero probability on the idea that it's actually, first of all, not the same thing as the things you've seen, but something new, and then kind of generating new concepts. And that's something that, models with a closed world assumption doesn't support. And so I think there's a formalism for trying to tackle this in a very nice way. And as we think about test time reliability, I actually think this is sort of one of the most promising paradigms for attacking this problem. Okay, so I spoke about algorithmic approaches for test time point-wise reliability. Let's talk about human-driven, because this is actually kind of cool, and one that, especially if we're at a machine learning meeting, we love, like, sort of doing things where we can write some math and write a pretty paper, and it's all good. If it involves human and user studies, we get very scared. So here, there was a really cool study where somebody did, they built this thing called Beat the Machine, where the idea was on a web page, they wanted to be able to figure out whether the, sort of the page had hostile language or not, okay? And the reason, or hate speech. And the reason they wanted to do that is because, well, in this case, people want to advertise, and they don't want their product to be sitting next to a web page with hate speech. So the idea is you want to be able to know confidently if something is hate speech or not, and if it is, you definitely don't want your product next to it. So the cost of misclassifying a page as hate speech is really bad. But turns out, you could use these sort of test time measures, but the thing that Adarsh spoke about was this notion of, like, there are many scenarios where the model, using our current methods, there are models that will say, I'm very confident that I'm right, except you're wrong. And so these are sort of the most severe cases, right, where it's hard to, even if you were to if you were to deploy algorithmic approaches for discovering them, unless there was a human in the loop, you're just not going to discover those errors because you're so confident it's right. Unless there's another form of feedback, you have no way of discovering it. So the idea of these crowdsourced discovery methods is he basically built sort of a game using Mechanical Turk to be able to crowdsource ways to identify failure points. In this case, what are types of pages that tend to be hate speech that my particular system happens to be bad at recognizing. And what they found after doing the study was that when they were using this sort of crowdsourced machinery for crowdsourced mechanism, they detected some of these more severe cases where the algorithm would have confidently said, no, I was right, but actually it was hate speech. The hardest to discover examples were discovered more often when they used this crowdsourced approach than using, which is sort of intuitive, but so something to make a plug for as we're thinking about failure detection approaches, to start thinking about human-in-the-loop approaches. And there's a whole sort of now emerging literature in trying to think about how do you use human-in-the-loop to do failure analysis. And if your system is in use, basically you have a natural human-in-the-loop already, and the question is you can use your logs, maintain them, and figure out a way to update. So that goes into my last and final section, which is monitoring for errors. Maintenance. How do we do maintenance? So we spoke about point-wise reliability and that being an easy source for being able to find and identify errors. And now that we have these errors, the question is, well, how do we know? How do we update the system? Do we update frequently? Do we update not so frequently? But actually, more importantly, is one that people tend to underestimate how hard it is sort of this notion of when you're using the system, you've deployed the system, you're collecting data. In some scenarios, there's a notion of a feedback loop. So you really want to build. Previously I spoke about shifts. You want those ideas to come back here when you're trying to do learning on the go, because if you don't, you're actually going to learn models that may misbehave. So when you're doing this continual updating, the science of continual updating in its own right is challenging and important to think about carefully. Let's see. So, and then, of course, AI systems integrate many components. Errors can accumulate. We need a sort of way to think about that, and accounting on tackling ML technical debt. So there's actually a really nice paper that I point to there, and it has sort of a very nice description of in practice, when you deploy these ML systems, what are the kinds of issues, what are the places of technical debt you collect, and what are the maintenance issues you need to be thinking about? Okay, so with that, I hope I gave you sort of at least some framework for sitting back and thinking about as we're building, especially we want to be responsible and we're building in safety critical domains. It's really important for us to be thinking harder and harder about not just sort of what's that thing I can download from GitHub and what's that data set I can download from GitHub, which I don't have to at all say in this community. You guys are very mindful. There are other communities where this really needs to be hammered in. But download your model and you run it on some data, and then basically you write another sort of snippet of result, and then you're done. And the challenge is then it gets picked up by the press and then gets sort of written in all sorts of wonderful ways. And then before we know, we have superhuman powers and we've totally solved the world's problems, and then we've created new problems for ourselves, right? So we really need to be thinking harder about, what are the sources of failure? How do we build methods to prevent these failures? How do we build monitoring methods to monitor them, and obviously corresponding design interfaces, and then also reporting practices. And with that, my final last few slides, which is I think one of the things that's interesting here is we tend to gravitate, at least so my upbringing is in the core machine learning community, and we tend to gravitate towards mathematical tools very quickly. And we like things that are easy to study and easy to work with. Because probability is something we know how to work with, it makes sense. The thing is, it's only one tool for describing uncertainty and the concept of risk. And we need to become more creative and broaden our arsenal of things we use. And one of the things about sort of using probability as a tool is that basically it's always conditional on a set of assumptions. And the bigger problem, I think, in our scenario, a recurring theme in my talk should have been everything we did relied on assumptions. You had to draw your graph, you had to draw your specs that you wanted, and then all of the methods were conditioned on that. And so becoming more mindful of what your assumptions need to be is so important. And that really requires understanding your domain, caring about it. like caring about the results. Who's going to use it? And so, this is sort of an interesting story, the Fukushima nuclear disaster that happened. The issue was they sort of thought, well, why didn't we get anything right? Turns out they'd made certain assumptions, and all of their safety protocols were conditioned on those assumptions. But the problem was that the assumptions were just wrong to begin with. So the assumptions were violated. So, having this mindfulness around assumptions is really useful. Finally, beyond sort of new methods, are there sort of other resources like data sets where we can benchmark this, and this sort of remains, like people are now starting to put out data sets for like trying to measure against adversarial attacks and perturbations, and that's sort of one, but maybe there are other, I'm actually sort of, maybe this can help to some extent, but this sort of does that version of like, don't care about the assumptions, don't care about the domain, take a data set, now your goal is to do empirical performance optimization on this new data set. So to me, this feels like this is really important, but it's important for people who are already mindful. But I worry it also gives a tool for many to be not mindful. And then, thinking about, in terms of practices, approaches, this notion of risk conceptualization, is often domain specific. So going back and thinking about what that is, and then in terms of like common practices, we need preoccupation with failure. We need to be obsessed with it. We need to be thinking about it. We need to have reluctance to oversimplify. So sort of this notion of like, we find a formulation that sort of works. I know the fairness community has been totally plagued with this because you sort of find a formulation that you think is a good formulation of fairness, and then before you know, there are 8-page algorithms optimizing that fairness criteria, and there was never the right criteria to be optimizing to begin with. And this is sort of true even in the interpretability community. Like for a long time, people said, oh, let's make a model interpretable, then hundreds of papers on interpretable. Well, it turns out now there are recent papers showing being interpretable it can actually be dangerous. In some cases, it doesn't help you at all. So I think kind of being a little bit more mindful of like not wanting to oversimplify, but just understanding and caring about the domain is sort of quite important. And then another one is deference to expertise. Now, I hate the word deference, but deference to expertise is interesting because sort of there's knowledge across the table. When somebody knows more about the domain than you do, it's actually helpful to learn about it. It's actually helpful to not sort of want to succumb to this idea of like black box techniques that, and maybe that is the right thing to do, but you at least want to understand what the desired specs are and what are you trying to accomplish. And yeah, concepts and ideas highlighting the importance of continuous. So these are just principles I've drawn from the reliability engineering literature that I think are very relevant to us and something that they think about a lot that I think needs almost like part of our culture needs to change in the way we approach these problems. And I spoke a lot about reliability. People think, and this is very distinct and different from, say, privacy, fairness. Fairness is much more about figuring out what's the right thing to do, not necessarily, reliability is given you know what you want, you should at least execute flawlessly. Let's not be prone to failures that are unanticipated. Versus fairness is, figure out what's the right thing to do. And that often involves like discussing and understanding what do we want as a community. There's a value function there that needs to be considered. Security, so like some kinds of issues are around, so this is unrelated to failures from security, failures from abuse, which is, misuse of a system where somebody is purposely trying to attack, that's transparency, policy level issues that need to be considered in order to prevent failures, and then finally system failures, where there's a very literature. So to wrap up, ensuring reliability is all about given desired behavior, ML components behaving as intended and not accident prone. I mean, in the very least, we need to get this right, because it's kind of weird, because we're talking about far more complicated things, and we can't even make our systems behave the way you expect it to behave in these scenarios. And this sort of, we broadly taxonomize this as sort of 3 areas, borrowing from the reliability engineering literature, which is prevent or reduce likelihood of failures, identify failures and their causes, and then fix failures when they occur. And with that, thank you. There's sort of a link here, we will post these slides, but the link will have sort of a much more extended and expanded list of references. And if you find some that should be included, that weren't included, please send us a note. And with that, thanks so much for listening. It's 6:26. I won't be insulted if you have to leave, because it's between me and I'm between you and the drinks. So, and I'm around. You can email me or ask me questions. I'll be around for another 10, 15, 20 minutes. So with that. Any questions? Yeah. 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 Yeah, that's a great question. So let me summarize. So the question is, Adarsh, by the way, you're welcome to come in, join me, and take some of the questions. Um, so, um, so the question was, how do we think about this trade-off between, you're ensuring safety, which may require compromises on performance, and performance as in thinking about it as like accuracy. Okay, so this accuracy versus safety trade-off. So this is a really good question because actually there is a trade-off in some scenarios. And I think one way to think about this is safety is actually a desired spec. You have to set that up front. Like being unsafe is not sort of being unsafe to certain kinds of failures is not sort of like, wouldn't it be great if it's a requirement, right? And most fields outside of computer science, like for instance in healthcare where I do a lot of my work, this is an absolute requirement, like failure is not acceptable. So in other words, I kind of think of it as one type of, the safety requirement is where you say, well, I absolutely need this kind of failure, and then condition, safety, I need to failure proof it. And now condition on that, there's a second piece here, which is now condition on that, we need to build methods. So like I gave you that example of the surgery estimator, which means it gives you an optimal model condition on it, right? So now, the next place you have to think about is, well, maybe I can collect better data, right? So at that point, condition on like whatever safety guarantees or safety, properties you need, then you're asking, well, can I still do better? And still do better often means in practice, can I collect more data? Can I collect better data? Can I collect more informative variables that I hadn't previously thought to cover? Does that answer your question? There was another hand, yeah. I can paraphrase the question, that's fine.
Hello? There we go. So you talked about detecting adversarial examples at some point. I was wondering, you talked about anomaly detection and using methods from that field for detecting adversarial attacks. But you can't, have you tried using a discriminator from a generative adversarial network to do that? Because that's exactly what that's trained for, in a sense.
Should I take it or do you want to take it? Okay. I kind of want to step back. There are lots of ways in which you can attack a problem. And often one way to think about it is, each method comes up with its own set of assumptions. Like under what assumptions does it work? And then what are its guarantees, right? What types of things can it detect? And so I think my goal was more to, I think what we need to do is sort of more frame the conversation as test time, point-wise reliability, right? So this notion of like, per test point can we measure point-wise reliability? And now the question is, how do we measure that? I actually think that could be domain dependent. So it'll probably depend upon the data. It'll depend upon the data means the type of, the density of the data, how much data you have. So that was the density principle. It'll depend on the model, which we showed was the model local fit principle. And it'll probably also depend upon the domain because you may actually have some additional requirements that may be domain specific. And then when we think about other methods people are doing, often they're taking into account additional intuition they have. So additional intuition about either for a given model choice in a high dimensional space, there are certain methods that are better or worse. Or for instance, they know something about the data, very specifically about the data that they can exploit. And so I think the choice of what's the right approach is dependent upon these three things. Well, what data do I have? What do I expect to hold? What model do I have? And then do I have any other criteria? And, like when people are trying to do open category detection anomaly, they have some additional assumptions. Like for instance, the kinds of data they're trying to detect are like distinctively different. Like essentially it's a whole new concept, which means it's very far away, which is very different from say a perturbation, which is, it's in the same density, but it often occurs in high dimensional spaces. So has a different sort of requirement.
I had a question, which is, you talked quite a bit about techniques, tools and techniques, and I sort of wonder how these things relate to, I guess, the practice of engineering, the practice of building these systems, and how you would relate them to, for example, laying out requirements or otherwise figuring out sort of when you should use particular tools at what point in the practice of designing and building a system you would actually deploy things, and how you would relate that to workflows.
I'll take this one because this one's a favorite of mine. So I think this map is an example, right? So I feel like I kind of think everything has to start from like, what's your goal? Like, what are your assumptions? What do you know? Right? So it doesn't start from the tool, it starts from the question. Like a lot of times people do research by starting from the tool. I have a tool, I have this model, and now I want to apply it to a new data. That's different. Like that's like starting from the tool to answer a problem. Like that's backwards to me. I think maybe it's not. Maybe in certain contexts it's a fine thing to do. But let me step back and sort of shift your attention a little bit to the vast world of problem solving is not like that, right? Effectively, you have an open-ended problem. It's a hard open-ended problem. And so the first thing you're starting from is like, what's the question? What are the assumptions? What do I need, right? And we could play this game in a, and so I sort of did that in a very toy sense in the pneumonia thing, right? So you're writing out, well, what are you measuring? What are you trying to answer? What's your graph? What's your spec? What do you think the assumptions are? What the variants are? And then you go through each of these error sources and you ask this question. Is this an issue? Is this an issue? Is this an issue? Is this an issue? And then that kind of dictates what types of things you need to be worried about. And then from this paraphernalia, like, this tool chest, which ones do you pick and choose and in what order? And then finally, some of these are very much like data dependent, right? What models, model specification. Some of these are agnostic, where if it's a problem, you're going to use these class of methods. So that's one. And then similarly, being mindful when you're then, once you've developed something and then you think, you check your assumptions constantly. Were my assumptions right? Have I learned something new about the world to believe my assumptions weren't right? And in other words, revisit all of it from scratch. Or so figuring out ways to build tools to test your assumptions or measure whether your assumptions are right is very important. And another thing that I think probably people do in some way or another within large companies, but I would say there isn't a whole lot of literature around it, and these are not sort of things we like to think about because it's not cute. It could be. I mean, we just haven't made it.
Okay, so I have a question kind of in your failure prevention section. When you're talking about the causal models, you had maybe some examples that are very binary, right? So the backdoor criterion thing, or you find variables that you want to exclude. But is there any tools to maybe think about a particular variable and kind of have some, measure a number for the amount of tolerance you have for a particular variable? So it's not so binary as to remove the variable entirely.
Do you want to take it?
This kind of relates to this idea of like we're doing sort of talking about worst case analysis and like this idea of being distributionally robust. It depends on how you define sort of like the set of invariances or what you want. So for example, you could consider saying that I think that shifts are only going to be of this much strength. And now that actually, so adding more information there, saying that I think that these pieces are going to change by this much. And it's in the same sort of idea, just now instead of being sort of arbitrarily distributionally robust, you have like a bounded notion. So there's some sense of like, I'm making guarantees for shifts within this amount. Does that?
Yes, so there are tools that you're able to.
Yeah, and so I would suggest looking at our paper to get sort of references for also, like we talk about this difference. So in this safety critical application, maybe we care about worst case and we want complete invariance, but there's also cases where you're more willing to hedge bets or you have more information, and so then there's tools for sort of optimizing models like that, yeah.
Actually, I'd be really curious to, if you have an example, not now, but like right after, if you'd like to draw it out, I'd love to talk about it, because I think my view of the world is that I think there are very few things where if you know the world is this way, then you want to either protect from it altogether or not at all. Like our notion of like we want to protect from it 0.5 is a very strange thing. The issue where the uncertainty comes in is we just don't know if the world is this way or that way. So the sort of like uncertainty is not in whether if the world is this way, should I protect for it or not? If the world is that way, should I protect for it or not? The uncertainty is more in our understanding of which way the world is. And right now people confuse the two, they conflate the two. So they think they need to do sort of half, because they're not sure, they need to go halfway. But that's not what they need to do. They need to figure out how to do sensitivity analysis to these two different worlds.
So you mentioned several times that you need to understand your domain, which sucks because no one likes to hear that they have to understand the problem they're working on. But we know we have to, and we try. For example, the case of pneumonia with the X-rays. I don't know the history of that specifically, but I can imagine even if you understand the problem very well, you still miss it, right? And you also did mention maybe you don't have a perfect model of your world, but is that, or maybe are there cases where that's the kind of thing that can be detected? Because you talk about once you detect it, once you know that exists, here are some methods for addressing it. But are there ways to find out these like sort of completely unseen, surprising facts about, or basically failure modes to detect them in the first place, where you had really no idea that they were happening, even if you understood your domain?
So I think, so good question. Here's sort of a couple of ways to think about it. So the first thing is, I think we had, so in reality, what I've found is if you really want to tackle a domain, it's not really a version of like, you did it all at once and then you're done. It's the version of like, you can be as mindful as possible in order to determine something. Now, if it's a safety critical domain where the cost of failure is high, you can't willy-nilly deploy, collect some data to see where it fails, come back and then fix it, right? You're going to be watching it like a hawk to see, collect data to see where it's failing and then fix. So in other words, essentially in like some of the other disciplines, like again, clinical trials is a good example, or like safety protocols that people implement now. To be fair though, I don't think those are great either, but they do better than what we do, I think. But essentially this idea of like, when we first built this graph, this looked nothing like what I'm describing here. Like over time, as we've, now this is our 6th year of working on this problem. And as we've worked more and more and more on this problem, we've discovered places in which things fail, which then inspire what the correction should be. And the methods for like point-wise reliability is a way to discover on-the-go issues. So that's one type. The ways to, like human in the loop, that's often a very common type. But it's sort of like exercising the system. It's the common version of like, you're either algorithmically exercising it or you're human-wise exercising it, but you're exercising it to figure out where there might be failure cases. And then ideally, you can almost always save yourself time if you just go talk to an expert or learn about the domain, because then you can save yourself a whole bunch of energy by imagining catastrophic things that maybe you would never discover from like rare events that you just wouldn't discover in examples.
I think we're about 2 minutes over time, so we should probably wrap up. Let's thank the speakers one more time.
Thank you so much.